Урьдчилан ихтэй эхлүүлэхэд би Англи Батик сургуулийн математик инновацийн төвийн төвийн судлаач Adwaye Rambojin гэдэг залуу ярих юм. Батик сургууль бол Монгол улсын сургууль болон энэ манай судлаачтай хөлбөмбөж нэлээд олон жил ажиллаж байгаа тийм газар байгаа юм. Өөрөө математикийн дэд 1000 гаруй хүнтэй яг статистикийн доктор баг зураг гэдэг математик статистик төр чиглэлээр хүчтэй тийм сургууль байгаа. Англи дотор яг статистикийн докторийн сонголтын төвтэй зөв сургуулиудын нэг. Adwaye бол 2016 онд Монголд бид манай ихтэй сургуулийн багш нар болон судлаачид зөвлөсөн өвгөтлийн ухааны судалгааны ажил гэсэн тийм сургалтын семинар хэрэгцээ ажиллаж байсан юм байна. Тэрнээс хойш байнга хамтаар Монгол төсөл хэрэгжүүлээтэй ингээд явдаг юм хамаа. Өнөөдөр бол мөрхөө судалгааны ажиллаа тийм байна.
Hi everyone. Is this my cue to start? Can you all hear me? Okay.
Yes. Okay.
Can everyone see this? Because I can't see you. Yeah, okay, so I think you can see this. So today I'm going to talk a little bit about Gaussian processes and how they can use for they can be used for shape modeling. So this is some work that we did with the National Health Service, which is the NHS. So it's the National Health Service of England. And at the university, 2 centers were involved. So Samba, which is a doctoral training center where I am from, and Camera, which is a research unit in the Department for Computer Science. So I'll start by talking a little bit about Gaussian processes and try to give you a little bit of intuition of what they are. So essentially, Gaussian processes here in this slide, I denoted by F, is a random process, is a random function, sorry. So if I take a finite set of points, so for example on the picture here, you look on the x-axis and I evaluate this function at these set of points, then together the function values will be normally distributed. And a Gaussian process is determined by 2 things, just like a normal distribution is parameterized by its mean and covariance. For a Gaussian process, you instead have a function that describes the covariance between 2 points. So for example, if I'm looking at here on the x-axis 0.2 and 0.6, evaluating this function k here gives me the covariance between the function value at location 0.2 and location 0.6. Similarly, if I were to evaluate this mean function that I denote by m at location 0.6, I get the average value that the function takes at this location. So essentially, you specify the form that the function will take, so the smoothness of the function, by specifying the covariance function. So here on this slide, I give an example of a covariance function, but to sort of understand really what a Gaussian process is or how you can use it in machine learning, it's good to think of a regression problem. So usually if you have a regression problem, you have your response and you wish to find a function f that describes what's happening between your input and output pair. So because Gaussian processes are of a very general function class, you can choose to model f as being a Gaussian process. So let's say you're faced with a regression problem and you have some data that you wish to relate via some function through supervised learning, then what you need to do to basically fit this model is decide which form this covariance function is going to be and what you want to do with the mean m. So in general, for the mean, you could estimate the mean function by choosing some sort of basis expansion. So for example, if you're looking at the splines, this could be one way of doing it. Or if you're lucky that the relationship between t and y is linear, then you can fit a linear regression here. As for your covariance function, this sort of represents, as I said earlier, how smooth your function can be. So for example, here, this ensures that the function is quite smooth, because it's sort of, if you look at the decay, if you fix t here and you sort of increase s so that s moves away from t, you can see that the covariance between the two starts to decay quite smoothly. So for those of you who are familiar with some math finance, this, for example, you can a Brownian motion is, you can interpret it as a Gaussian process with a covariance function that is different from this one. I think it's something like a minimum of t and s, if I'm not mistaken. So if you're fitting your regression function here, your set of parameters will essentially be the parameters of the mean function and of the covariance function. So I denote these two by theta m and theta k here. So just like for any supervised learning problem, you usually have some sort of loss function to minimize, so as to fit your function to your data. So in this case, we're going to be the loss function is going to be the negative log likelihood, and this is the negative log likelihood of a multivariate Gaussian. So the only thing that I did here is, I replaced the mean by the mean function evaluated at the locations t. So the locations t here are basically your independent variable, or the input to your supervised learning task, and y here is the output. And the matrix A here is basically the covariance function that I introduced earlier, corrupted by some noise. So the reason why, so this is the identity matrix multiplied by some variance, and the reason why I use the identity is because we assume that the noise is independently distributed and there's no relationship between them across the locations t here. So the cool thing about the Gaussian process, in my opinion, when you're doing prediction, is that you're really now starting to get into the Bayesian philosophy, where you observe some data, you have some prior knowledge about the data, and in this case, we think that the data has some sort of Gaussian structure. You observe some data, and then once you observe the data, you correct for the observations that you've made. And this is the whole philosophy of a Gaussian process. So here I have a Gaussian process that has mean 0, and I've observed data y, and now I'm at a new location t, where I observe I want to know what the value of this y star is going to be. So t star here is some new data that we got for our supervised learning problem, and we want to do some prediction. And the way you do the prediction is, instead of looking at just one value, you get a distribution at the location t. So this distribution is going to be Gaussian, and the Gaussian will have mean given by mu star p and k star p here. So these two formula here are well-known formula for the posterior mean of a multivariate Gaussian distribution. So just to sort of show you what I mean by the fact that it's Bayesian and you sort of adapt your knowledge, here is a Gaussian process prior that I've set, and I haven't optimized the hyperparameters. So on the right then is the same Gaussian process, but the line here is instead showing the posterior mean. So the posterior mean at every location of this indexing set here. So in this case, the problem we were looking at, it's a very simple toy problem, is basically the how fast people complete a kilometer in a marathon. And this has decreased over the years, which is what the data is showing. And as you can see, at first you had quite a flat prior on what about your belief, but then when you compute the posterior mean, it actually fits the data quite well. And in addition to this mean value, you also get a little bit of an error band that is shown here. And this error band is basically the posterior variance that we just computed here. Okay, so I hope you sort of have a good intuition for what a Gaussian process is now, because now I'm going to step it up a bit and introduce a dimensionality reduction technique that relies completely on Gaussian processes. So I'm going to spend a little bit of time on this picture here so that you understand what's happening. So right now we're moving into the unsupervised learning task. So you have data, and the data has dimension n, so you have n data points, and each of those data points has p features. So if this is the dimensionality of one data point p, and the task here is to basically try to represent this data in a lower dimensional space. So I am going to say that, for each data point of dimension p, I'm going to represent it by a latent point of dimension q. So if I want to do this using Gaussian processes, I'm going to introduce something called a Gaussian process latent variable model. So in this model, what you do is you look at each column of this data array here. So you're looking at each feature across the whole data set. So let's say I'm going to introduce that a little bit later, but if I say that y are the outlines of some shape, which is the whole point of this talk, then I will have n outlines, and each outlines will have a certain dimension p. So each coordinate in this outline here across the whole data set will be modeled as a Gaussian process. So this takes a little bit of time to get used to, because previously we were looking at just one feature, whereas now we're looking at multiple features. So that's the first thing we do. So this diagram here is sort of showing you what's happening. So I have n data points, and for each of these data points, I will have one realization of this feature. I assume that for each of these features that I have, for each of the data points, I will have one latent point, and this latent point will be the indexing set for Gaussian process across this feature space here. So that's the first thing we do. And the second thing is we assume that these lines that I'm showing, that you can see in this diagram, they're independent from each other if you know what the latent variables are. So to adopt some Bayesian terminology here, YP, where P is the column of the data set, so it's the individual features, is going to be independent from each other given the latent point variable t. So that allows us to now write a data likelihood, because what I now have to do is I just basically multiply the previous likelihood that I showed you together, and this is what I get. So if you now have a task where you want to fit a Gaussian process latent variable model to your data, what you need to do is basically optimize this cost function here with respect to the latent points and the hyperparameters. So the hyperparameters theta would be the same thing that I showed you earlier. So if we usually would not have a mean function because we assume that the mean here is going to be equal to 0, but we definitely will have a covariance function that will have certain parameters to it, and you optimize all this in one go. So I'm going to now go to the application of this model, because this model does not need to be only used on shapes, but you can use it on any task that requires you to reduce the dimensionality of your data. So as I said earlier, my y now, so this is what you can see on the bottom left, is going to be one example of the data set. So this is one outline. So I will have multiple outlines like this. So I will have multiple realization of x0 and y0. And if I look across the data sets, I will have n realizations of this first coordinate here. And this first coordinate across the data set will behave as a Gaussian process that has an indexing set. So each data point will have its own latent point variable, latent space variable t. So on the bottom right here, what I'm showing is basically, I'm trying to, so the important thing here is that we want to capture the variation in shape. So if I give you an outline here, x0 and y0 for this outline is starting at the point where my mouse is pointing here. But for another data example, it might be starting at the location where x10 and y10 is starting. So what we want to do is, across this data set, wherever we want the coordinates across the data set to represent the same area on the bone outline. So as you can see here in the red box, the coordinate I'm pointing at here should really be at the top of this ridge here. So the way we do this is we basically define an optimization problem where the energy that we're trying to minimize is representing the curvature across the whole data set, across the whole coordinates. So what I'm trying to do is to basically, for each of these points here that correspond to each other in the vector of outlines, I want their curvature to be the same. And once I minimize this, I see that the points align onto each other. So this is just to explain to you how this is done. And I thought it's a good thing to mention in this talk for completeness, because if you don't do this, then what you might end up capturing in terms of variation might not be due to just shape, but might be due to things like where on the outline you position your point. Right. So now that you know how to fit a GPLVM, which is short for Gaussian process latent variable model, we can look at how you can generate new shapes from this model, because it's not just a dimensionality reduction technique. It also allows you to generate shapes that you haven't seen before. So similar to what we were doing earlier, if I give you a new latent point position, then there should be a new shape that's associated to it. And the way in which we find the shape is by looking at the posterior mean. So we use the same formula that I introduced earlier, and this is what you get. So on the diagram, what you can see here is actually a latent space that has dimension 4. And on the left, the shape here, the number of points on this outline was something like 110. So a space of dimension 4 is able to represent and generate an object that lives in a space that has a dimension of 110. Well, it's actually 220 because there's the x coordinate and the y coordinate as well. So what I'm showing then in the middle and on the right are slices from this space. And this is me moving around this space to generate new shapes. And the heat map that you can see on the latent space is actually the posterior variance at each of these locations. And the dots that you can see are the training data that I used. So this was fit on a bone from a hand X-ray, and the data for that was recovered from the local hospital here in Bath. So I got a rheumatologist who was my PhD supervisor at the time to draw around some outlines to generate the data that went into this model. So it's all good that we have a way to reduce the dimensionality of things and we can generate things from this GPLVM, but does it have any other applications other than this? So I'm not sure if you're familiar with this architecture, but it's quite famous in the image segmentation literature. So this architecture here is called UNet, and the aim of UNet is, given an input, its task is to give you a mask that represents the presence of different objects. So it's supposed to segment it. So in this case here, there's an index finger, and if I put the index finger through this UNet architecture, it should give me the location of the individual bones, or rather, the mask that represents where bones should be in this image. But the problem with this is that it's not always, it does give you some sort of mask, but it doesn't locate exactly where the individual bones are. Whereas we, on the other hand, have a model that can give you the exact shape of bones. So the whole idea now is to merge these two models and to try to get a better output from a hand X-ray by using both the shape generation process and this UNet. So the way in which I do this is I generate a distance transform based from this UNet architecture, and what I now get, this map that you can see on the bottom right, basically gives me the distance from the edge set, so from the edge of the bone. So it's not very accurate, but what I can now do is try to evolve this shape here onto this distance transform until it lies on the level set that is equal to 0, so until it lies on the edge. You can do this very easily via gradient descent, and the resulting model is called an active latent space shape model. So it's actually an extension that we did on a model called the active shape model, which is a very old model which was introduced in the early 2000s, where you sort of have a bunch of points that you want to evolve on a potential, and that potential is basically usually a distance transform from an edge set. But the problem is that if you're just evolving a bunch of points, then you get stuck on some local minima. Whereas here, we're not evolving a set of points directly. What we're actually doing is we're moving around in the latent space to generate a shape, and then we see whether this shape matches onto this potential set. And in this way, moving through the latent space guarantees that we have a shape that actually represents the object that we want to segment. So this is the intuitive explanation of what is happening here. But for those of you who are familiar with Bayesian networks, this is what is being shown here. So you have two different things. There's a GPLVM, which each have their set of parameters. So there will be the shape parameter here, and at the same time you have some pose parameters. And the whole idea of this Bayesian network is to give us is to explain the relationship between variables so that we can integrate the inner bits. So the bits that we actually integrate out would be the unit architecture and this bit here. So I'm not going to go into too much detail about how this is done, but I'll show you some results instead. So this, what you're seeing here, is basically showing you the error, or rather the distance that the outline is from the real contour that it's supposed to segment. And it's showing, I'm showing that for 4 different bones on the hands. So as you can see on this diagram here, well, actually on this diagram, I don't know if you can see that, it's a bit too small, but I'm looking at the metacarpal, the proximal phalanx, the middle phalanx, and the distal phalanx. So I was trying to basically segment these 4 bones out, and this is the error for each of them. So the individual lines here are basically represent the types of potential that we have used. So the red one with the dots here is the one where we use UNet, and the others are 2 different edge detectors. So one of them was a straight, a very simple edge detector that was based on finite differences on pixels, and this one was a different deep learning architecture where instead of looking at the image as a whole, we were classifying patches into whether they were bone or not bone. And the very bottom one here was generated by looking at the ground truth. So the actual outline of the image was used to generate the potential I showed you earlier. And then what we did, we evolved a Gaussian process latent variable model that had a latent space dimensionality of 2, 4, 6, 8, and 10. So the interesting things here from this diagram is that whatever the bone you're looking at, using UNet actually reduces the variance that you have in your data set. But in bones that are difficult to segment, just like the metacarpal, which is the bone right in the middle of your hand, you get better results in terms of accuracy. The other thing that's interesting to see is that after the dimensionality of Q equal 4, you don't get that much improvement in accuracy if you increase the dimensionality of your latent space, which again shows you the power of Gaussian processes. The fact that you're sort of reducing the dimensionality of your data non-linearly allows you to use a space of dimension that is much smaller than your actual data set. And this highlights the power of Gaussian processes for dimensionality reduction. So this marks the end of my talk. I've got some references that you might want to use. So if you want to understand what Gaussian processes are, there's an amazing book by Rasmussen. It's called Gaussian Processes for Machine Learning. It's available online, so you can actually download it and read it. You don't have to buy it. And Gaussian process latent variable models was introduced by Neil Lawrence. If you want to, do some explore this area, then I suggest you read this paper because it builds on previous work by Mike Tipping, who was exploring another method of dimensionality reduction. And if you want to look at the model that I described, but at the end of this this presentation, then you can read the paper that we published, which is called Active Latent Space Shape Model. I think you can have it, read it on my website. So if you Google my name, there should be like a University of Bath website where you can get this paper. So as I said earlier, this work was done mostly when I was doing my PhD, and this was at the doctoral training center at Bath, which is called Samba. And this research was also supported by the NHS and the Camera Research Center, where they do a bunch of cool motion-related research. So with this, is there any questions?
Энэ үеийг шүүний анаач момент. So with the improved segmentation using the active shape model, can you actually get better results for diagnosis?
Sorry, I was sharing the wrong screen all this time, but
Yeah,
so this is something that we're still trying to figure out, because for the work that I just showed you, we only had data for the index finger, and we're actually annotating the whole hand now. And just to sort of talk a little bit on this model, so the fact that we had only the index finger didn't just affect, well, it actually didn't quite affect the shape model, but it affected the potential function here, because we were only able to generate this unit potential for one finger. So if you want to use it on a whole hand, there's a bunch of extra steps that you need to take to fit the shape model. So the first thing that you need to do is you actually need to build a shape model for the entire hand, so that you're able to initialize the positions of each of the shape models. So by having this, we're able to basically figure out where you should have those outlines initialized, so these outlines initialized before you start your optimization. So this is what we're hoping to do now, is to basically move this into the stage where we're trying to see if it's better or not than human readers.
In order to give more context, I'll explain a little bit about your previous work on this topic. In that, in Garni, Atlas гэдэг үгшний төвшин тодорхойлох тийм судлаар ажиллаж байсан байна. Тэгэнгүүт хэд асуудал гарч байгаа юм. Нэг нь бол угаасаа тэр амар олон үгшний дата авах хэцүү болж байна. Одоо хүний мэдээлэлтэй маш их асуудал болж байна. Тэгээд хоёрдугаар нь дата байсан ч гэсэн тэр одоо нэгдүгээр чинь дата байдаг янз бүрийн инпутээр авсан дата байхгүй. Эдгээр машинууд calibration нь өөрөө үүсдэг. Дахиад өөр ажиж байгаа. Нэг үгүй шууд авч байгаа. Дээрээс нь одоо энэ өнөөдрийн ярьсан зүгээр тэр зураг модельд оруулж байгаа харин гарах гэсэн юм бол ийм асар их зураг явуулсан. Тэгээд илүү сайжруулах цөөн зургийг ажиллах бол наасаа ер нь бол эдгээр зурагнаас ясныхын яг хэлбэрүүдийг зөв гаргаж байгаа. Угаасаа энийг эмч хүн яаж хийх вэ гэхээр ясын ингэж шуумж хэмжээ хийх юм байна. Тэгээд тэр цаг хугацаанд яаж үүсгэж чавах ясын хэр үүсгэн байдаг гэсэн юм эсвэл жигсэн байх томсон байх гэдгийг хэмжээ явуулдаг. Тэрийг нь бол Thank you.
Thanks for having me.